Now let's see if we can make a regression where we're going to try and predict the amount of weight people will lose based on their height. So to do this, we can use XLSTAT, modeling data, linear regression. It's going to ask us for what we're trying to predict. We're trying to predict weight loss and what's our starting variable. We're going to use height to try and predict that. So that's our independent variable or explanatory variable or X variable. We have names. Everything else can stay the same. All right, and we're done. And this is our output. Just going to add the zeros here so it's a little easier to read some of these things. Okay. So let's start with the top. We have 277 observations. Great. R squared is the proportion of variance explained by the model. That's 24%. It's not bad for having one variable. One variable explains 24% of the variability here, so that seems pretty good. Let's look down here. This is our ANOVA. And for ANOVA, we care about this value here, the F value. We want it to be large, and it is. And that is showing us that overall, the model coefficients are unlikely to be 0. The null hypothesis is that all of the values here are 0, and since we got a really high value, that's rejecting that null hypothesis and suggesting that at least one of these values is not 0. That means this model is potentially useful. All right, now for interpreting our results here. We have an intercept, so this is our beta naught, beta 1. What this is saying is that for every inch taller you are, the expected weight loss increases by 0.8 pounds. That's pretty high, but great. And this is statistically significant. We can tell here that number is higher than our critical value, which would be about 1.96. This value is, you take your beta 1 divided by your standard error. Okay, that's where this value comes from. All right, and we can see our range, just lower bound, upper bound, 95% confidence interval. Because we used XLSTAT, it tells us the equation here. So delta hat is equal to our intercept plus the beta 1 coefficient times height. All right. Let's see if we can do slightly better by adding an additional variable. I'm going to go back to XLSTAT, linear regression. And this time, in addition to my qualitative variable of f, I'm going to hold down for me Command on a Mac and add Jillian and over 40. So we added 2 additional variables, but our R squared did not go up much. It means that they didn't help explain very much. Let's take a look here. All right, so height remained statistically significant. Jillian is barely statistically significant, and over 40 is not statistically significant. We can tell here the t-value is very low. The corresponding p-value is very high. So that's telling us that this value could just as well be 0, right? and if it should be 0, then we should remove it from the model. It gives us the model output here. Let's go ahead and remove over 40, so I'm just going to repeat this process. And I will use height and Jillian. So looking at the proportion of variance explained by the model, it's 25. Remember, with just one variable, it was 24, so this doesn't help much. Let's take a look at these. You can see that it's on the cusp of not being statistically significant. It is significant, but it's not, it's close to not being significant. And what this would mean is that if you have Jillian as your trainer, then your expected weight loss increases by 1.5 pounds on average. So holding your height constant. And if you want to interpret height, you would say a 1 inch increase in height is associated with a 0.83 pound increase in weight loss on average, holding constant whether or not you had Jillian. We can see our F value is very high again, so the whole model makes sense. These values are unlikely to be 0 altogether. All right, so that was regression, simple linear regression with one variable and then with two variables.